So welcome to the Picture Language Seminar. It's a real pleasure to have Sasha Geim. She is going to tell us about a fault-tolerant architecture for computation.
Yep. Okay, yeah, thank you. And I guess thank you for the invite to give a talk. So yeah, today I'll talk about some of our fairly recent work on quantum computation with digital atoms very broadly. So yeah. Okay, so as we know, there's kind of a promise to have computational advantage with these quantum systems. And the main challenge is how to counteract errors and decoherence. And this kind of goes back to a debate in the 80s and 90s on the physics of information. In particular, it was noted a long time ago that when analog computation, even in the classical sense, is more powerful than purely digital computation, but the key challenge is how to correct errors. So you fundamentally can't distinguish some small kind of over or under rotation from your intended small kind of analog computation. And then when people thought about how to do quantum computation, this problem came back because quantum computation is inherently an analog process. And to give an example, if you think about how we make ourselves robust to errors in noisy classical communication, what you would do, you would have some zeros and ones, some digital bits, and these importantly, they're digital, so you kind of don't have anything between your 0 and 1, and they're corrected by dissipation. So in kind of this way that a transistor works, you dissipate yourself either to the 0, or to the 1. And so even with small errors, you'll go back to your intended state. But the key thing is that when you encode some logical state amongst these physical bits, the logical state also is digital. It's also a 0 or 1. So then the fundamental question is, how can you combine this need to have some fundamentally irreversible process, some dissipative process to have error correction with kind of unitary analog computation? And that's exactly the framework that quantum error correction gives you. It allows you to do unitary logical computation constructed from these dissipative physical states. And what this looks like is you have some physical qubits in whichever is your favorite encoding, so the toric code, color code, LDPC code, whatever you would like. And then on the physical level, you have dissipation via stabilized measurement. So this projective measurement kind of acts as this dissipative process, which takes like small arbitrary errors all the way to 0 or all the way to 1. And then this also makes sure that your errors are digitized and correctable, so that either bit flips or phase flips. At the same time, on the logical level, your computation remains analog. So you still have this analog logical wave function that allows you to do this unitary analog computation. And this fundamentally is different from the classical case because of the underlying physical entanglement. And so we can now have this ability to correct errors. It does, however, come at this cost of significant complexity and many constraints. So there's this qubit overhead problem, you need low error rates, you have restricted logical operations, control complexity, long runtimes, so on. And you have to consider the hardware and the control that you're going to use. So for us neutral atoms, but ions, superconducting qubits, whatever you would like. Then the logical encoding and decoding that you'll use, and then also the algorithm design. And you also can't consider these individually, you really have to consider them as a whole. And this leads to the question of to design an efficient architecture for quantum computation, you really need to understand the core mechanisms that are allowing you to keep the entropy low and to protect your algorithm output. And so our approach, yes, go for it.
So a very nice question. What kind of quantum algorithm can you realize for torrent using your quantum code?
I mean, in principle, anything.
I mean, like for example, the short algorithm, can you realize it?
I mean, we're not at the scale where we can really do like something very meaningful. I mean, the largest number of logical qubits we've worked with is 96. And that's in this specific high rate code where logical operations are kind of like a challenge, but that's where the research is right now. It's like kind of combining this like efficient encodings with logical gates to try and see what algorithms you can do. You can start to do things like scrambling, and like start to look at things like that. But yeah.
For example, like for the basic unitary gate, like the quantum Fourier transform,
Mhm.
and do you realize it's fault-tolerant, or what kind of size of quantum Fourier transform you can realize it fault-tolerant?
I guess the challenge with the QFT in particular, as an example, is these small angle gates. So having like controlled like root t, controlled like t to the quarter, and doing those fault tolerantly like has a very large overhead. So I don't know off the top of my head the resource estimates, but probably you could think about doing like 3-bit or something like that. But then as soon as you start going down to these very small angles, it also becomes a question of how do you generate those? And like what's the most efficient way of doing that?
I see. And is the hardness is because the control rotation is somehow not teleported, so you need it.
Say that again.
So I mean, does the hardness come from the control rotation gate, and not like the stabilized gate or clipping?
Yeah, I mean so I guess like
Maybe you could repeat.
yeah, so I guess the question was, where does the hardness of these small angle controlled gates come from? And it's just you're going up and up the levels of the Clifford hierarchy. So if you're thinking about topological codes, you're going to need to go to higher and higher dimensional codes, and that just typically incurs more overhead. Yeah, so like to have a transversal, if we're talking about transversal gates, then the other approach is kind of injection and distillation, and then that comes with its own kind of thinking through the considerations of that.
I see.
Yeah, but we'll see examples. Yeah. Okay, so maybe going a little bit onto the experiment side. So our approach is using reconfigurable arrays of neutral atoms, and the key features being non-local connectivity. So this enables transversal operations, efficient parallel control, and high fidelity single and 2-qubit gates. And in case you haven't seen before, just to go through an example of what programming a quantum circuit looks like, semi-arbitrary example, but key components, you have entangling gates. So you would have some kind of entangling zone, which is illuminated by the Rydberg lasers, which you pulse to do 2 or 3 qubit, or in general multi-qubit gates. And then you reconfigure your gate sites by moving the atoms around, so only atoms kind of next to each other will undergo a gate with each other. And okay, this is a little bit out of date, and I will mention some newer results on this towards the end, but kind of more than 99.5% CZ fidelity. Then you have single qubit gates, so these are fully programmable. Global 5e-5 error for bipulse, and then local is a little bit lower, just because it's technically more challenging, but this is really truly arbitrary. And then final component is readout and mid-circuit feed-forward. And I will also talk a little bit about the readout in particular. Okay, so in this work, we really kind of put together all the technical and also kind of QEC components to start to study what a fault-tolerant architecture looks like. And I'll start with talking about one of the very fundamental components, which is syndrome extraction, and really how to be below threshold and how to keep this entropy of your logical qubit low. And the architecture we use here is, so we have around 450 qubits. There's a storage zone where you can store your logical qubits relatively free from error. The entangling zone with long-range connectivity enabled by atomic motion. And then that's where you would do your 2-qubit gates and your fully programmable single qubit gates. Readout, both at the end and also mid-circuit. And this importantly enables, or a new thing in this work was qubit reuse. And then a reservoir, which allows you to refill atom loss mid-circuit during your computation. And yeah, so as I mentioned, one of the key things,
Sorry, I'm a little confused. So when you do the measurement, the qubit, the constant will be destroyed, while you can reuse the qubit.
Yeah, so you're reusing the atom in some sense. So you're very much like measuring the quantum state. but you can, for example, preserve the quantum state of some atoms and then measure some others because they're like done in your computation, or you're injecting it, for example, and you're doing a teleportation. So you want to measure those qubits and then you feed forward the logical state, but then these atoms, you still have them. So now you can reinitialize them and recall them or reset them and use them as like a resource in like continuing to do your computation. Yeah, so one of the key things in this recent paper was a new approach to readout. So conventionally, what you would do is, okay, you need to read out the spin state of the atom. If you just image the atom, it doesn't tell you anything about the spin state, so you need to convert spin to something. And what you would previously do is convert spin to loss. So if you have 0, 1, state 0, you would see atom present. State 1, the atom, you would resonantly heat it up and then push it out of the trap, and then you wouldn't see it. This does mean that you don't distinguish state 1 and loss, and also on average you lose 50% of your atoms, both of which are a little bit sad. So then what you want to do is lossless state resolve readout, and in particular this allows you to distinguish 0, 1 and loss, and also retains the atom essentially all the time. And so then you can do this mid-circuit reuse of atoms to allow you to have more qubits. And the approach that we take is spin to position conversion. So state 0, for example, here goes to position up, state 1 goes to position down, and if the atom is in neither position, then it was a loss. And the way that this works is with a 1D optical lattice that's state selective. So the 0 state is bright to the lattice, so the lattice provides a very strong confining potential. And then state 1 is dark to the lattice, so it doesn't care. And now if you bring in another tweezer and try to pick up the atom, if it's in the bright state, it's pinned in place, so you can't move it. If it's in the dark state, it doesn't care about the lattice, so you can just freely pick it up and move it. And in that way, you separate the, you move the atom according to its spin state, and then you can just image normally. And yeah, so this enables both loss detection and you retain the atom. And as we'll come to later, it allows this mid-circuit qubit reuse. And as a visual example, this is what gravity oscillations look like read out by spin to position conversion, so oscillating from left to right. So, okay, one of the key component of error correction is syndrome extraction. And so that's the first experiment that we study here, and in particular using the distance 5 surface code. So we have the entangling zone up here, shown with the data qubit block and then 1 block of ancilla qubits, and then there's more ancilla qubits down here in storage for later rounds. And what this looks like is you take your 5x5 grid of data qubits, bring in your ancillas, and then to measure here the weight for stabilizers, you do your 4 gates. So you move your ancillas and do a gate at each pair, and then you take your ancilla block away, and then here just measure that at the end. So you store it up until the end. And then you can understand firstly, what is this syndrome extraction actually doing? And to do this, we inject some error. So just kind of apply some Z rotations between syndrome extraction rounds. And what you find is there's 2 mechanisms for suppressing error. So there's this Zeno effect. So because you're doing regular projective measurement, you are kind of converting these coherent errors into incoherent errors by the projective measurement. So now you kind of have linear in theta rather than quadratic in theta error buildup. And then secondly, because you've now measured your stabilizers, you can track those errors, and that kind of removes entropy from your quantum system, and in some sense takes it onto your classical processing, and you keep track of it in your decoder.
So I'm very confused. How do you move the entropy?
So
what does entropy mean?
Entropy here means essentially qubit state errors. So if you have a bit flip, your logical state, you want to have no errors. Mm-hmm. So in the lowest entropy state, and then if you have errors, that's starting to introduce entropy. And if you know about where those errors are by keeping track of them in your decoder, in that way you know the state of your logical qubit perfectly. So it's as if it's error free. So it's low entropy. So this kind of removing of errors by keeping track of them in the decoding is this removing of kind of qubit state entropy. So I mentioned that we have this loss detection, and it turns out that loss is kind of a very key error source in neutral atom computation in particular. So another experiment you can do here is taking these repeated rounds of syndrome extraction, and you can look at the correlations between detection events. So here, detection events being when you detect the stabilizer flipped between two rounds, so you know you have error. And so one of these 24 by 24 blocks is one round of syndrome extraction, so measuring the 24 stabilizers and then looking at the correlations in just like a covariance matrix. And then these off diagonal are kind of spatial correlations when you have some physical qubit error, which lights up two stabilizers, for example. So these are space-like correlations. Then you can also see there's this kind of additional structure, and these time-like correlations are exactly because of leakage, or in this case, because of loss. And so this strong stripe here is because of stabilizer measurement errors, which create time-like errors between rounds. And then you also have these additional kind of time-like errors because of loss. And so you can see that when post-selecting on loss in this, so this is taking the 5% of shots with least loss, you can see these errors go away. And then if you take the shots with the most loss, they're very strong. So these correlations are really generated by loss. And so atom loss is playing a major role, and you're kind of getting this blinking pattern because you now have anti-computing stabilizer checks, which propagates in time. So you really want to be able to detect the loss effectively, so you know what was actually an error and what is just kind of this fake signal of your atom was lost. And so using this loss information in repeated error correction, here we're looking again at the distance 5 surface code, now with 4 rounds of stabilizer measurement. And it's a little bit of a confusing picture, but this is what the readout looks like. So I think there's a block of 5 by 5 data qubits, and then 2 ancilla blocks here, which are interleaved next to each other, and then another 3 ancilla blocks here. And then each one is either in 0 or 1, depending if it's down or up. And then if there isn't an atom, it's a loss. So that's kind of what the readout looks like for this experiment. And again, I think I mentioned already, detectors, we form detectors between the measured stabilizers, and if you see a stabilizer has flipped between 2 rounds, that's an error. So forms your detectors. And then you can look at the detector error probability. And if you don't have loss information, then it's roughly 13%. And then as you include loss information in several different ways, you start to see that this error goes down. And this is really because this loss information is reducing the amount of unknown errors that you have in the system. And one thing to highlight is this kind of formation of superchecks. So I mentioned that you kind of get this blinking pattern of stabilizers that form time-like correlations. This is because if you think about losing this data qubit in the middle, now this kind of 3 qubit check is anti-commuting with other stabilizers, so it's going to be randomly plus or minus 1. And so if you try and measure it, you're going to just get a random value. However, if you know that this atom is lost, you can product together this check, and now you can recover a weight 6 check, which is deterministic again. So this should always be plus 1. So now this again gives you reliable information about your errors, and these kind of larger weight checks called super checks. And this is this bar here. So putting that all together,
Before moving on, so I'm a little confused. Why do you need to consider like the correlation matrix between the stabilizer?
So you don't consider that in your decoding, for example. It's more just a way of understanding kind of what is the loss error doing, and why does forming these super checks, for example, help you? Like what's it telling you? And it's exactly that it's getting rid of this effect of having anti-commuting stabilizers, which form this like time-like correlations.
Okay, so in general, you don't need to consider it, but for this kind of uncombinatorial
Yeah,
stuff.
like it doesn't go into the decoding, for example, but you can, it's quite a nice way of, for example, comparing your theory and your experiment. So like when we were trying to figure out the error model, one like very nice check was that your simulated, like your simulations with the simulated error model produce the same like error correlation matrix as the experiment. So it carries a lot of information about your errors.
I see. So for example, in your experiment, like what kind of error you can like uh get from the correlation matrix? Like
Yeah, so I guess, I mean, it tells you a lot. So these off-diagonal ones tell you in particular about your measurement errors, because these are just ancillary measurement errors. And then, okay, I guess the strength of these tells you about just your like bit flip and phase flip errors, which are the ones that you're detecting with your syndrome measurement. And then these off-diagonal ones are telling you about your loss and leakage out of the state. And you can probably be more quantitative than that, but that's already like heuristically telling you the different components. Okay, yeah, so then, yeah, looking now at the logical error after decoding, I guess comparing distance 3 and distance 5, we see that this is now kind of below the threshold, meaning that distance 5 is better than distance 3. And in particular, again, the loss information is very important. So if you just use MLE, so yeah, another plot, loss information is very important. So this rightmost point is all the data. And then if you do a sliding scale post selection on loss, you see that the error goes down, which makes sense because a large part of your error is lost. And you can look at two types of decoder. You can look at the most likely error, MLE, so this algorithmic decoder. And without loss information, it's just a little bit below threshold. And then you can also augment it with loss information, and it goes kind of roughly to 1.7 times below threshold. You can then also use machine learning decoding, which has two advantages. So firstly, even without the loss information, it has the ability to pick up on correlations, or at least that's our understanding, is it's picking up on correlations induced by the loss. And then if you explicitly give it the loss information, it does even better. So then it gets you to this like 2.14 times below threshold. And then on a very practical note, it's kind of 4 to 5 orders of magnitude faster than these algorithm decoders. So it's just very practical for kind of use in experiment. And so for this specific 4-round characterization circuit, we find that we're about 2 times below threshold. You expect some small differences, so kind of 10 to 15%, depending on whether you're doing this with transversal gates between these syndrome measurement rounds and a kind of when you're going to the infinite round limit rather than the 4-round limit here, but kind of scale of 2 times below threshold is the correct number. And then you can also look more carefully at the error budget that you get out of this. And I guess main takeaways, the error distribution in experiment and from simple simulations, just using kind of an uncorrelated noise model agree very well. And it's very Poissonian. If people have seen kind of back in 2023, when we were working on high fidelity gates for the first time, we noticed that there were some correlations between gate errors in the benchmarking sequence. And it turns out that that was kind of a property of that particular benchmarking sequence. And that if you have gates very close together in time, then so one of the error mechanisms of the 2-qubit gate is black body decay. So your Rydberg state will decay to some nearby Rydberg p state. And now this p state can interact with your s state via dipolar 1/r cubed interactions, which are much stronger than your intended van der Waals 1/r to the 6 interactions. And so this can cause correlations on, and the lifetime of these states is kind of scale of 100 microseconds. So if you do your gates very close together, then this can cause correlations between errors of adjacent gates. But in a practical circuit, you typically have like 200 to 400 microseconds of time between gates. So naturally, these p states will decay before you get to the next gate. And so it turns out it isn't a problem in this circuit context. And then yeah, the other takeaway is that our leakage errors are very strongly dominated by loss. So there's some very, very small contribution, for example, scattering error. But then if you reset your qubits in the circuit, you're also gonna get rid of that, which we'll talk about later. Yeah, and then, okay, right now we're 2 times below threshold, but okay, with some improvements in the CZ gate, which you can see here is kind of 40% of the error budget, this will shrink. And then also there's pretty clear routes to shrink these. And then I think, yeah, somewhere around 5 and maybe a bit better times below threshold is pretty achievable in the midterm. Okay. Unless there's more questions, we'll move on to kind of the next part of doing quantum computation, and that's now doing these stabilized measurements, but in the context of logic operation. So at least with neutral atoms, there's 2 ways that you might think of doing logic gates, and in particular with transversal gates. What this looks like is you have here again your 2 distance 5 surface codes, and then you interleave them, do a C0 between every pair of physical qubits in your logical block, and then that does so here a C0 on the physical level does a C0 on the logical level. And so the logic gate is realized directly between the data qubits in this step. And then you will follow that with some syndrome extraction with ancillas in order to remove entropy, so to detect your errors and do this kind of projection. The other approach you can take is lattice surgery, which is much more common in planar architectures. So, for example, superconducting qubits. And here, the logic gate is a Pauli product measurement, and this is done with your ancilla measurement. So now the stabilizer measurement and the ancillas are not just removing entropy from your data qubits, but they're also performing the logic. And to look a bit more closely at that, you can prepare a Bell state between these 2 codes. So either with a transversal C0 or with a Pauli product measurement. And if you look at the sensitivity to the ancilla measurement error, so here just injecting error in post-processing, the transversal C0 case, so making a Bell state in this way, is really quite insensitive to ancilla measurement error. And that's because all it's doing is removing entropy from your data qubits, and you're not affecting the fidelity of your logic operation itself. If instead you use this lattice surgery approach and now you get these measurements wrong, then it really starts to matter, because these ancilla measurements are doing your logic. So you're directly kind of impacting the fidelity of your logic operation. And so this is what leads to this typical order D rounds of syndrome extraction per logic gate for fault tolerance, because you need to also be robust to distance D in your ancilla measurement errors. And that's kind of true for the lattice surgery case, but if you use correlated decoding, it turns out you don't need that in the transversal case. And in the transversal setting, you're only balancing this rate of entropy creation by your logic gate and entropy removal by your syndrome extraction. And looking a bit more quantitatively, you can vary this ratio between the amount of syndrome extraction you're doing and the number of logic gates you're doing. So here, now with transversal gates, doing some repeated C0s, syndrome extraction round, repeated C0, syndrome extraction round, repeated C0s measure. And then depending on how many C0s you do per round, with some kind of sliding scale post-selection, you find this minimum. And this optimal of 3 C0s per round is very consistent with theoretical predictions, roughly coming from the fact that you have 4 C0 gates per stabilizer measurement, and then 1 C0 gate per transversal gate. So 1 to 4, 1 to 3, that's roughly where that number comes from. Then kind of from these experiments, we also learned a lot of lessons about decoding, in particular that to make yourself insensitive to these ancilla measurement errors, which you really shouldn't be sensitive to because they're not affecting your logic. You need to make sure that you're always looking at the logical stabilizer rather than the logical qubits. And then finally, this experiment also makes it very clear that logical gate fidelity is not really it's not like a single number. And that is just, this is not a horizontal line. So the error per logical operation, the error per gate, is dependent on the number of gates you're applying. So it depends on the density of errors that's in your system already. And so altogether, leveraging these transversal gates and then combined with correlated decoding, you can reduce the number of rounds that you need to do from this traditional order D, the fault tolerance, to order 1. And this can start to lead to really very significant speedups in large computations. Okay, so now we have how to remove entropy and how to do transversal gates, but the kind of final ingredient for your algorithm is you need a universal gate set. And this is one of the key challenges with error correction is you now have this ability to correct errors, but you've lost the ability to do arbitrary gates. You now have this discrete gate set. And in particular, Easton-Nil theorem tells you that some single code can't have a transversal unitary universal gate set. And so what you need to do to have universality, at least in the transversal case, is you need teleportation. And the example we look at here is using the 3D read-Muller code, so the 1513, and this has a transversal T-gate, so a transversal 45-degree Z-rotation. And an experiment you can do is prepare this 1513 code in plus, and then just apply a physical Z-rotation to all your qubits, and then do single qubit tomography. And what you find is you have these plateaus at the T and the Cliffords. And this exactly corresponds to having a logical transversal T-gate. You can repeat this experiment with other codes. So in particular with the 2D color code, which does not have a transversal T. And yes, indeed, you find the plateau disappears and you only have logical Clifford operations. You can also do it with unentangled physical qubits. And again, you don't have really any transversal gates. And then interestingly, you can do this with the read-Muller code prepared with the wrong stabilizer signs. So here by applying X flips to 4 of the qubits to make all the Z stabilizers negative. And then you again find that all these robust logical T's disappear. And this is telling you another role that the stabilizers are now playing, which is they're making sure that you have the correct underlying physical entanglement structure, such that this kind of interference of all these different, of the phases on all the different physical qubits comes out to give you a logical T. So you need to have +1 stabilizer signs now for logic. And when doing these kind of non-Clifford gates, at least on non-Clifford on the physical level, you can't just track your stabilizer signs as you would in a Clifford circuit. And another thing that you can see, so I guess going on from this point, that the physical entanglement structure is kind of very fundamental for these transversal gates, is you can do a thought experiment. So in particular, if you try to do an error-corrected Bell test to kind of test for the quantumness of your system. So if you have Alice, who has a logical qubit, Bob, who has another logical qubit in a Bell pair, if you measure in the X and Z basis, your correlations are not going to be distinguishable from classical correlations. So if you want to kind of see the intrinsic quantumness, you need to measure in the T basis. So you need to have a transversal T. And so what this is telling you is that you really need to have the correct entanglement for error correction, and kind of that's a really quantum properties. And okay, you can do this experiment. So here, taking a read-Muller code and a Steen code, making a Bell pair between the two, and then measuring in these kind of T dagger and XY bases, and that allows you to calculate the CHSH inequality, and you find that it does indeed saturate within error bars of the quantum bound of 2√2. And this is very related to a lot of work that people have done on the link between computational hardness and the need for physical entanglement. It also kind of points to the fact that the 3D code, this like measurement of the 3D code, is what's giving you the logical non-Clifford. So here, this experiment you could interpret as measuring this guy in the T basis and this guy in a Clifford basis. You could also interpret it as teleporting a T onto the Steen code. And then this is kind of a building block to teleporting some logical non-Clifford into your circuit, for example, or at least one of the approaches that I take. And so, okay, now we have a transversal. Yep.
So here the reason like the T it is relatively independent because in the bill it is because in the CHSH test the x plus y square root 2 over square root 2 is just exactly the up to some phase is exactly the rewriting the T gate in the polybasis.
Maybe I don't follow. I agree that x plus y.
Yeah, because in the if I remember correctly, the measurement in the FH in probability is like x plus y divided by square root 2.
Yeah.
And then this is exactly
exactly.
That's the reason you use say H to claim the Bell test out the entanglement is
Yes, yeah. So in the SH inequality, I mean, you can measure in any bases, but then to have something that's like violates the classical, that's larger than the classical bound, you need to measure in something that's not the 90 degrees bases, and the maximally violating one is this T basis. So this 45 degree rotation, which gives you this 2.
I see. But this somehow rewriting the stage. Is this like the connection between entanglement and the magic? It's universal relation.
I guess it's saying that in order to do a Bell test with logical qubits, you need to have this correct physical underlying entanglement. And so if you want to have that, it is kind of like doing a classical computation on qubits. Like you're not really leveraging the quantumness of your state, but as soon as you start doing something non-Clifford, then you are doing something that's intrinsically quantum on the logical level. Okay, so yeah, we have now the transversal T, and like the ability to teleport that into your algorithm. And so if you want to have some small angle, kind of something like what we were talking about earlier, one way that you can do that is via kind of what the Solovay-Kitaev theorem tells you, which is that you can generate arbitrary angles with polylogarithmic overhead, for example, through a sequence of Hadamard T gates. And what this looks like with the Reed-Muller code is, okay, have multiple codes for pattern and plus, apply a T, and then teleport that onto your next Reed-Muller code, and this teleportation both teleports a logical state and also teleports in a Hadamard gate. And then you can repeat that, so then another T, another H, another T, another H, and so on. And then what you find is that you start to exponentially fill the Bloch sphere as you kind of do more H's and T's, and you start to, yes, with polylogarithmic overhead, reach all these small angles. And this also tells you that with transversal gates, this transversal teleportation is really a key primitive. So you are doing everything transversely, and you do have a universal gate set, and that's really enabled by the fact that you're teleporting the state to get this final, in this case, the final Hadamard that isn't a transversal gate on the Reed-Muller code.
So the reason you need the teleporting the TK, the Hadamard gate is because for this 3D rhythm code, H cannot be realized.
Exactly. Yeah, H is not transversal.
But for other stabilized code, the T gate cannot be realized transversally. So people also can teleporting the T gate. So like what's the difference like teleporting the Hadamard gate?
I mean, you could choose one or the other. It kind of depends on which code you want to work in. So you could kind of inject your T and then teleport it in through a magic state factory, or you could like do it on your Steam code and then, or on your Reed-Muller code and then teleport that onto your Steam code and then use your Steam code for methods. Kind of, it doesn't matter how you're preparing one gate or the other at a very fundamental level. It's just that you're always going to need to teleport in something. So here you're teleporting in the Hadamard, in other cases you're teleporting in the T.
I mean, that's the cost to teleport the Hadamard is almost the same as the teleporting the T.
Yeah, I agree. Yeah, and I mean, this is one approach. You might also kind of do this with surface codes and like inject and distill and then teleport that in, or with Steam codes or something else.
So is it the last state in this teleportation chain that will get like the rotation that you desire?
Yeah, exactly. So kind of this last qubit is in whichever state, and then the exact angle that you choose is whether you do or do not do these feed forwards. So you choose the feed forward x's in the correct way to target your specific angle. Okay, so then with all these ingredients, you now look how to go to deep circuits and kind of what computation looks like there. And so far we've talked about this physical qubit state computation, so these bit flips and phase flip errors, and we've seen that syndrome extraction will help you remove them. There's also these other type of entropy and these other types of errors in your atomic state. So in particular, your atom can get hot, it might get lost, it might leak out of the qubit subspace, and these are also types of entropy that you need to remove from your logical qubit and from your computation. And on an algorithmic level, the teleportation natively accomplishes this, because when you do this measurement, you're both obtaining stabilizer information of your code, and then you're also kind of measuring your atoms. So now you can reset them, you can recall them, and you can reuse them. So that's both kind of the first part, removing the physical qubit entropy, and the second part, removing this atomic state entropy. And then on a hardware level, we also developed some new AMO tools, which I won't talk too much about, but feel free to ask. And in particular, in order to preserve coherence on some active data qubits while measuring some others, a key thing is that you need to be in a finite magnetic field, because the magnetic field is what allows you to isolate like your qubit states. And typical imaging approaches don't work in finite magnetic field. So we developed kind of this scheme for 1D polarization gradient pooling, which does work in finite magnetic field. And then also, as you're imaging, you need to make sure you don't scatter photons off the atoms that you're trying to preserve coherence. So we added this kind of 1530 nanometer beam, which was first used in Vladimir Vilich's group. And that essentially applies a very large light shift to your excited state, so it strongly shifts your atom off resonance from these imaging photons. And together, these tools really enable you to have steady state, kind of constant entropy operation, where as you're doing your computation, you're removing both this physical qubit state entropy via your syndrome extraction and removing your atomic state entropy via this recalling and reinitialization. And this is kind of like a fridge. So you have your computation, which is nice and cold, and then this teleportation and syndrome extraction, you're removing this physical entropy, and then you're recalling and reinitializing your qubits, and also refilling loss from the reservoir. This kind of goes in a cycle. And an experiment you can do to study this is essentially repeatedly making, here's steam codes as a first example, and making 1D and 2D cluster states out of them. So in particular here, we start with 16 steam codes in kind of group A, and then another 16 steam codes in group B, and then you can entangle between them. And now, for example, if you're making a 1D cluster state, or if you're teleporting your logical state from group A to group B, you now measure group A because they're done in your computation, and then you can take these atoms, which you've now kind of used up, and you can recall them, reset them, and then reuse them to make more steam codes, and then entangle them with group B. Now group B is done, so you measure, you reset, you recall, and then reuse group B up here, and in this kind of alternating fashion, which is very reminiscent of MBQC, you can kind of go to very deep circuits with just these limited physical qubit resource. And as kind of a movie, what one of these like A-B teleportation layers looks like is you prepare your steam codes here with a hypercube encoding circuit. The ovals are gates. Then you make here a 1D cluster state in space, entangle with another block of steam codes that's already in a 1D cluster state to make a 2D cluster state in space and time. And then you measure out this first block. So this is what the measurement looks like when it's 50-50 random. And then, okay, this is the longest part. Then, okay, you've measured, now you can recombine and now recall and reset, and then you would start again. So you would go and make new steam codes out of these guys and entangle them with these guys. And doing that, you can make a 2D cluster state of steam codes. So here showing the stabilizers of the logical 2D cluster state. And so, okay, at layer 1, you make scene codes, then you measure them, and then you entangle them with layer 2. You measure, and then you reuse those qubits, you entangle, and so on. Yep.
How long does this process take?
So each layer here was 43 milliseconds, which is pretty slow. So for example, the syndrome extraction, one round was 2.4 milliseconds for the circuit. The main thing was, to be honest, idle time, because we were using desktop computers, so there was just a lot of latency. So that could probably be like several times faster if things were optimized.
I see. And what's the coherence?
So the T2 is like 2 to 3 seconds, and the T1 is about 10 to 15 seconds. And the vacuum lifetime for us is around 10 seconds, although a lot of experiments have it slightly higher. So it is a small part of your error budget, these kind of background effects, but you're typically much faster than that.
I see.
Okay, yeah, so it keeps going. And then, okay, so now we're starting to do these deep circuits via kind of continuously teleporting. And so on the logical level, what this looks like is you have unitary evolution by this teleportation, while on the physical level, you have this continued measurement, which is dissipative and removing your entropy. You can kind of start to study this by looking at, so this is for a 1D cluster state of steam codes. If you look at your logical correlations, they kind of persist throughout your algorithm. So here looking at correlations between kind of a code at layer 0 and a code at layer 7, for example. In an error-free algorithm, these would all be +1 because you're just measuring your cluster state stabilizers. So with some like post-selection on acceptance fraction, you indeed see it's +1. So this is kind of your algorithm is leading to the correlations, which is output. And then in contrast, on the physical level, because it's dissipative, you have this very rapid decay of correlations. And so, because your errors are being projected as entropy is removed. And so teleportation enables both this universality with transversal gates. It also natively removes kind of both these like atomic state errors, so your atom being missing, your atom being hot, and so on, and also the qubit state errors. And then it's also very simple and very general. So in particular, it's very independent of the code details. You just need to have a CNOT between your code blocks, so any CSS code will do. And so you can think about using this for high rate codes, for example, and here using the 1664, which is also kind of has this hypercube encoding circuit. You see extremely similar features, so rapid decay of your physical correlations, while your logical correlations persist for much longer. And there's two things that you can do with these high rate codes, like kind of two types of new operation. In particular, because you now have entanglement, or because your operators are now supported on the same physical qubits, and there's this kind of underlying entanglement, you can do permutation gates. So simply by rearranging the physical qubits, you redistribute this in-block entanglement and generate logical entanglement. And then here, using a 2D cluster state, you can also kind of leverage the correlations between different qubits, between different logical qubits, because they're now supported on the same physical qubits and kind of have some type of error detection. Okay. If there's no questions, kind of going a bit more towards the outlook. So I mentioned the gate fidelity is improving. So this is something that we've kind of been working on up to last week. So this qubit reuse, another really nice thing is it enables fast calibration. And this is essentially, this is beginning part of your sequence, which is very slow. So this is to load your atoms from the magneto-optical trap and recool them, etc. This is slow. So you want to just do this like very fast part. And so with qubit reuse, you can just do this many, many times. And then you can do, for example, single qubit oscillation. So this is the real-time data rate, which is roughly 2 orders of magnitude faster than previous tweezer experiments. So this is really, really very nice for calibrating things quickly. And then it's going to keep playing. You can also extend this to 2-qubit gate calibration. So here with a 1D entangling zone, and then kind of randomized benchmarking, and then this qubit reuse and repeating this 80 times. We've now kind of got into CZ fidelities of 99.85. So compared to this like 99.55, 99.6 we previously were using. And the error budget is also very consistent with theory. And this kind of roughly 0.15% error, of a lot of which is loss, is also kind of potential, like having to also improve your single qubit fidelities, but that also there seems to be many places where we can clearly improve that, is pointing towards like at least 10 times below the surface code threshold, which is really pretty exciting. Maybe just because this is something that I've recently worked on, these kind of tools that we've developed for qubit reuse also go beyond error correction. And in particular, you can use them in quantum simulation. So here we developed kind of an analog digital approach. So using the Rydberg qubit for many body evolution and the hyperfine qubit for kind of arbitrary gates. And then you can study things like probing excitations in here just a 1D hopping Hamiltonian, but in principle, whatever Hamiltonian you want. And then we also studied a quantum spin liquid state, which would otherwise be very hard to probe in just the analog qubit. And you can start to access kind of these many interesting examples. And a lot of this was enabled by this qubit reuse because it just like, so dramatically speeds up your cycle rate. And that now you can like start to post-select and like look at observables that are just otherwise practically like you just can't get to. And then also highlighting some really nice work from Atom Ray 2. To go to really deep circuits, ultimately you will be limited by atom loss, which is never going to go away. So you want to have continuous reloading, and this is something that they developed. So kind of just having a continuous source of atoms to replenish your lost atoms, and then there really is no fundamental barrier to the depth of your circuit. So all these tools are kind of pretty exciting to how to, in the near term, get to large scale kind of QEC architectures. So yeah, summarizing, we've studied kind of the foundations of what algorithms with a fault-tolerant architecture look like. So in particular, kind of how to remove entropy, and then how to use teleportation for universality and physical qubit reset. Combining this now with a lot of the ongoing work, for example, how to do algorithms, so how to do fermionic algorithms, or kind of more interesting high rate codes. And then in the next few years, error rates will continue to go down. Hopefully we will continue co-designing. And so kind of figuring out what's this sweet spot between theory and experiment. And then with this continuous reloading, your atom loss is no longer a limit. So you can go to these really large scale computations and hopefully do things like Shor's, as you were asking about. And then everyone is also really excited about all these kind of new platforms and also kind of how to combine these different processes, for example, with optical links. So yeah, there's a ton of things to explore. And yeah, as I mentioned, some of these techniques are also pretty fun for kind of quantum simulation and maybe other things we've yet to discover. Yeah, so okay. Then thanks to the lab and Atom Ray 2, Martin, who was moonlighting as an experimentalist. Well, I guess he's kind of just really experimentalist these days. And then all our many theory collaborators. Yeah. Thank you.
Well, thank you very much. Thank you for a beautiful introduction to the experimental world, and exciting things are going on. It's clear that there'll be a great deal of interface between experiment and theory. So
Yeah, sure.
maybe we have some discussion now. Perhaps if you stop sharing, we can see the panel. There are a number of people online, and maybe there are questions here. Yes.
So what are the main bottlenecks that limits your fidelity, like technical bottlenecks, let's say?
I think right now every component by itself can be pretty good. I mean, there's always fundamental atomic physics things, but there's often always a way to improve them. So I don't like go further detune quantum laser or things like that. And so there's this kind of engineering challenge of laser power limitations. But then in practice, the thing is just like having everything working well at the same time and over a large scale. So homogeneity and like drift. And sometimes I don't know, you'll calibrate the single qubit gates really well in one sequence, and the two qubit gate really well in another sequence, and then moves really well in another sequence, and then you put them together, and somehow it's not the sum of its parts, and you have to debug why. And that's where like a lot of the challenge is, to be honest. It doesn't feel fundamental, but it's certainly like just effort and time. And you always discover a phenomena that you didn't think would matter, and then it somehow does. Yeah.
Yeah, I think an important concept is called.
Louder.
Yeah, I think an important concept is called break even.
Mhm.
But have you ever shown a break even in variable atom arrays in certain codes or something?
I think so. In this, we didn't really look too carefully. In the logical algorithms paper, we made, I guess, this Bell state with surface codes, which was just a tiny bit below break even, but like kind of roughly the same. It's also, I mean, it's an important thing, but it's really like a very like short depth thing. So like, how do I prepare a Bell state? Like that one Bell state might be a little bit worse than your physical Bell state. But then if you're trying to like do many of them and like continue operating, your physical Bell state is just going to keep getting worse because you have no way of removing those errors. But in the logical computation, you do have a way of removing those errors. So in some sense, it kind of makes, you should really think about these logical computations in like the deep circuit limit, where you're just going to keep building up errors, and they're going to win over physical computations where you have no mechanism to protect yourself. So it's a useful benchmark, but it's not like the pinnacle, I would say.
So you mean like we should think about the computation as a whole, not just like a
Yes.
single code? Like,
Yes, for sure. Yeah, you should definitely. I think that's a big lesson also with like this decoding of transversal gates. If you think about single codes as you would with like single physical qubit errors, you actually like do a much worse job. Whereas if you think about the algorithm as a whole, and for example, think about how your logical operator is propagating rather than just the error of your logical qubit, that's where you get this kind of order D round savings and you start to really benefit. Yeah.
Sorry, could you give a little explanation? What does the break even mean? Right?
Louder.
I guess the question was like, what does break even mean?
Yeah.
Just the kind of doing the same operation with logical qubits and physical qubits, your logical qubit does better. So it's complementary to saying you're below threshold. It's kind of a different benchmark of. So I don't know, for example, like Quantinium, I think have recently made T-states, which were like, I don't remember exactly, but scale of 10 to the minus 5 error, which is much lower than you would get for a physical qubit T-state. So that's beyond break even, and below like the pseudo threshold. Pseudo threshold again being the kind of error rate at which your physical and logical qubits have the same error. But so these are all very nice benchmarks for kind of saying like, where am I, and like tracking progress. But in terms of thinking about the benefits of the logical computation, they don't capture everything.
So we have a question online from Yifan.
Yes, hi. Thanks for the talk. So I actually have some questions about the slides on the quantum gate synthesis, the SK theorem slide that you present. So you mentioned that for you having around 3 T gates, you can already cover most of the area of the block sphere. But I want to know that what is the trade-off between the gate accuracy that you wanted to synthesis and how many T gates you actually can have in the, for example, a realistic quantum simulation experiment?
That's a really interesting question. I mean, I don't have a quantitative answer, but there is definitely a trade-off, exactly like you say, that as you're trying to make a smaller and smaller angle, you might be gaining precision if your gates were perfect, but you're also doing a deeper computation, so that has more errors associated with it. So at least to me, it does seem like an interesting question. Like if you're trying to make a really tiny angle, at what point is it better to just do nothing? Like at what point is that lower error? And yeah, I think these are interesting questions, which I think people are exploring theoretically. And I mean, in experiment, like the 3Ts was already starting to be kind of challenging, but I mean, the errors on this could also be like a lot better. So yeah, interesting question.
So Yifan will be a graduate student here in the fall, so you can collaborate.
Okay, I look forward to meeting you.
Yes. Thank you.
Yeah, so maybe following up my previous question, my question is very simple, just does the error rate in each qubit can be suppressed below the threshold of maybe surface code or something?
I mean, for the surface code for sure. I guess we showed that it was below threshold. For these particular experiments, it was not below threshold. They were challenging, and it was a first attempt. Also, the thresholds of these codes are not so nice, so you'll probably use something else. So I mean, these I don't remember. I don't remember exactly off the top of my head. The surface code is certainly below threshold, and everything else I think is more exploring the physics of kind of how you would approach these problems rather than necessarily yet being at the fidelities that you would want to ultimately be at.
So because it is below the threshold, actually we don't need to show like how low the logical error rate it is in the surface code, because having a low logical error rate in surface code does not mean that algorithmically you have a good performance compared to classical.
Yeah, I mean, I guess what do you mean by you don't have good performance compared to the classical?
No. I just mean that like we should consider algorithmically altogether everything, not
Yeah.
just a single.
Yeah, for sure. And I guess so for the surface code, we did this. Yeah. Yeah, so this experiment was just a 4-round like memory circuit, but then from simulations, you expect these like below threshold to carry over to if you were using this in an algorithm, okay, slightly lower effective threshold. So you wouldn't be 2 times below threshold, a little bit below, but you would still expect to be below threshold in the algorithm setting. And the challenge is now maintaining these fidelities in an algorithm. And I think that's kind of the next experimental frontier.
I have another technical question.
Louder.
I have another technical question. So, with the interplay between coherence time and the speed of your electronics in general, limit the scalability in this case, like how large your code's distance, for example, like would be, or any of these things?
It's a consideration. I think the typical code sizes that people estimate you need is say like scale of like a distance 20 surface code or like a few hundred physical qubits, 1 logical qubit. The slowest part of like neutral atom computation is the moves. So the gates are pretty fast. I mean, they're a much smaller fraction, and it's really just moving around that's slow. And I think that's something that we hope to make faster. And we'll need new technologies for that. But that's, I think, one like technical thing that needs to improve. Imaging is also on the slower side, and that's another thing that people are pushing for. So okay, assuming that, and I think it's a fair assumption that we kind of speed up a lot of these things. It's maybe like 5 to 10 times faster for like the algorithm than these current experiments. And then in parallel, you can also try to improve things like T2 and T1. So I mean, our T1, I said like around 10 to 12 seconds, but people have shown, I don't know, like an order of magnitude higher than that with like further detuned tweezers, for example. And then like T2 similarly, like ours is around 2 seconds, but people have shown like 12 seconds. So those can also improve. So the combination of engineering new techniques to make things faster and reducing your fundamental errors should make it essentially be not a problem. And it's part of your error budget, but like a sufficiently small part that you're still below threshold, I think is the main thing.
I see.
Yeah.
Well, thank you, Sasha, for taking us to the experimental frontier. We look forward to hearing more from you in the future. Thank you very much again.
Thank you.